So my plan for today is to follow from what we did in the last class and kind of just do a brief recap. But essentially, the idea is for the rest of the course, we will really be needing the sort of undeniable truth that electrons in semiconductors are really quantum mechanical objects, and we need to learn how quantum mechanics determines all that we can do with electrons in semiconductors. So I'm trying to kind of give you a little historical background of what led to the realization that we need to model, to understand electrons as quantum mechanical objects. Those of you who have had a lot of quantum mechanics, I hope you can also paint a picture based on solid state physics, because many times it doesn't get taught in this way. But I want to kind of also show how solid state physics or semiconductors or metals have led to a lot of also deeper knowledge in quantum mechanics itself. So it's kind of give and take both ways, right? So what we were talking about in the last class is this model of Drude, which explained electrical conductivity of model. And just to be clear, looking back in history, in the 19th century, 1800s and mid 1800s, people knew quite a bit about metals. People didn't really know much about semiconductors. And as far as the history of semiconductors go, I hope you have had a chance to read it. If not, the copies are here, and we'll. I think I'll. The first assignment is in the works. So one of the questions is to write a little short critique on this paper. So I think you'll read it anyway. But around middle of the 19th century, people knew quite a bit about metals. And we discussed these things in the last class, like for example, they're conductive, and they have both good electrical conductivity as well as good electrical conductivity. And they also have good thermal conductivity. They also carry heat very well. We're talking about metals. And the third part is that they're shiny or reflective, and that's another way to say they're, it's related to the optical conductivity. So there's conductivity all the way, electrical, thermal, optical, and this is something you're going to do in your assignment. Okay. So in addition to that, I didn't quite mention this part, but what in 1850s, a few researchers that were measuring electrical and thermal conductivity found for metals is that the ratio of electrical conductivity, which we saw in the last class how Drude explained that electrical current is electrical conductivity times the electric field, right? We derived this in the last class, and the electrical conductivity happened to be the number of electrons per unit volume, the density of electrons in the metal, electron charge square, times the scattering time over the mass of the electron. So that's something we found in the last class. This is the Drude model for electrical conductivity. This tau is the average time an electron travels between two scattering events. Q is the electron charge, electron density, mass of the electron. And you can see that immediately after the electron was discovered, Drude could explain that. And that's because till 1890s, nobody knew there was something called an electron, right? And they discovered it, and the mass of the electron was found, and the charge of the electron was found, and based on that, he could explain the electrical conductivity of most metals. Right? So, but that's really not all. That's essentially Ohm's law. We saw in the last class that explains, V is equal to IR and all that stuff, right? But Drude became much more famous, not just because of this, but because of something much bigger. What he explained was something that has really remained mysterious for half a century, and this is the experimental fact that people had measured. So if you measure the electrical conductivity of a metal and you measure the thermal conductivity of a metal, so let's call it sigma, and I'll explain the thermal conductivity in a little more detail today, and let's call it kappa, the Greek letter kappa, right? Electrical conductivity and thermal conductivity of a metal, and you take the ratio electrical conductivity by the thermal conductivity, right? Essentially ratio, and you divide it by the temperature, and this is actually a constant for most metals. Across many metals, you can measure electrical conductivity of the metal. If I measure 5 different metals, the electrical conductivities will be different. The thermal conductivities will also be different. But if you take this ratio with the temperature in the denominator, you get something which is a constant, and this constant used to be called the Lorentz number. And roughly 2 times 10 to the power minus 8. I'm going to use these units. I like volts, being an electrical engineer. So volts over Kelvin squared. That are roughly this number, 2 times 10 to the minus 8. And it's actually amazingly uniform across many metals. And this experimental finding was known and is still known as the Wiedemann Grand Law, after the people who had measured and kind of documented it for the first time. And it kind of really remained, and this was, I think, in 1850s or something like that, way before Drude. And what Drude did was took his model of an understanding that we have electrons doing the business of conductivity in metals, and he applied it, and he could explain this into great degree of accuracy, explain this for the first time. And what we'll see is what emerges from this story now is, remember, this is classical mechanics, there's no quantum mechanics yet. Just the fact that there are electrons that are subject to the laws of classical physics, to the laws of electromagnetism, to the laws of Newton's law of motion, and thermodynamics, classical thermodynamics. Based on that, what Drude showed was this quantity, the constant quantity, which is the ratio of the electrical and the thermal conductivity with the temperature in the denominator. That is equal to, and we are going to derive this today, and by Q whole squared. So he showed that it is equal to the Boltzmann constant, which is the heart of statistical thermodynamics, classical statistical thermodynamics, and at that time the newly discovered electron charge, right? So and the ratio of this squared, if you take this quantity, I think you can see right away that Boltzmann constant here is 10 to the power 23 joules per Kelvin, and electron charge roughly 10 to the power minus 19 coulombs, and joules over coulombs is volts, and there's a Kelvin in the denominator, this whole thing squared. So you can see, I get 1923, so 10 to the power minus 8, right, roughly. Right? So, and this is the first explanation of something that had remained mysterious for about half a century. And that's why that's kind of added a lot to why the Drude model was, in some sense, almost spectacularly successful, because it revealed and opened something up for people. Yes. Yeah.
Out of curiosity, was the charge of an electron found before the Boltzmann constant or after?
After. For sure. Yeah. So Boltzmann, much after. So electron was discovered in 1890, just around 1900. So, and then the charge by mass was discovered with this oil drop experiment right after that, and that sort of thing. So yeah, but much after. Right? And so at that time, this Q was new. KB was, Boltzmann had done his statistical and Drude actually used this to explain the Lorentz form. Yeah.
Wait, so that identity, is that equal to the sigma over KT?
Yep. Okay. That's right. Yeah. And we're going to kind of first see that, and how he came about to do this, and then we'll see that a couple of the assumptions, because if something is so spectacularly successful in explaining things, everything in it must be correct. But we'll see that actually by the end of the class today, hopefully, we'll see also that the fact that Drude was able to explain this is also very fortuitous, because he didn't know quantum mechanics. At that time, there was no quantum mechanics, right? But we'll see that there's a very interesting cancellation of things in the numerator and denominator. So if you consider the numerator and denominator separately, And people tried to kind of start measuring those, and then opened a whole can of worms that led to also the quantum mechanics itself. So I want to first show how this came along. Why? Because in this course, we will be very much interested in these quantities related to semiconductors. What's the electrical conductivity, mobility, transport, and how fast electrons move. We'll also be interested somewhat in the thermal conductivity. In fact, those of you who are interested in energy applications know that this is very closely related to what's called, for thermoelectrics, where you generate electricity out of heat. This quantity is very much deeply related to in thermoelectric devices like a ZT factors and all that. Okay. So, okay, let's go through the thought process. How do you think about thermal conductivity? We have already talked about electrical conductivity in the last class. We'll see we think about it in a very same way. In fact, we think about most conductivity in a very similar way, at least right now. And then when we kind of when we learn the tools of quantum mechanics, we will kind of come back to this and see how do I write electrical conductivity now that I know that electrons behave different laws, not just classical mechanics. So we'll do that today. Okay. All right, so any questions, any further questions here? So this is what we're going to first do today, explain. All right, thermal conductivity. Well, so what is thermal conductivity? Just like electrical conductivity measures the efficiency of movement of electrical charge from one point to another, right? Let's call it X. Thermal conductivity obviously would mean the transport of heat, right, from one point to another. And let's say I have a piece of metal, and this is the left side of it, and this is the right side of it. And this side is sitting at a temperature, say T1, and this side is a little colder, T2. And so there's a temperature gradient across the metal. Let's think that the electron density is uniform throughout. Electron density is uniform all across this X, and electron density is N, which is the total number of electrons divided by the total volume of the whole chunk of metal. So that's the volume density of electrons, typically of the order of how much for electrons in a metal? 10 to the power? Yeah, 22, 23 of that order, right, per centimeter cube, right? Right. That's the order of magnitude of electrons. Now, just to step back a little bit, essentially, if you take this result for metals and you apply the Drude model and you try to explain the ratio for semiconductors, it fails completely. And that's because semiconductors in this feature electrons behave much more quantum mechanically than for metals. So we will see that later. Okay. So so there's the temperature gradient, and now let's say the temperature is varying in some way. Maybe not. There's no pathological blowing up, and it's very smooth variation. And so what we want to find is again a current. We are always going to be interested in currents whenever stuff is flowing from one point to another, charge or heat. Always interested in current. But now we are interested in the heat current, not in the charge current, right? Remember, for the charge current, what we had here was initially what the way we thought about the charge current is we said, well, there's a number of electrons times the velocity times the charge, right? Electron charge. That was the charge current. But now we are interested in the heat current. But the heat current will also be transported by some particles. And we know that there are atoms in the solid, in the metal, meaning the core of the nuclei and all that stuff, the nucleus, which is much heavier than all the electrons combined. And then the electrons, which are much lighter, right? And both of these things can carry heat. Atoms can carry heat, and the electrons can carry heat too, right? But people also knew around, at that time that if you take an electrical insulator and you take a metal, both have roughly the same number of atoms. Right? But obviously the metal is way more thermally conductive than an electrical insulator. So the first assumption for Drude was, I'm going to completely neglect the atoms in the way of the electrons. I'm going to say that the electrons are solely responsible for carrying heat. Does that make sense, at least qualitatively? Why? What's the thinking? Because both insulators and metals have almost the same density of, and so they must have the same density of atoms. But at this point, Drude was thinking but because metals are much more thermally conductive, most of it must be carried by electrons. So the number of particles that are carrying my heat are exactly similar to the number of particles that were carrying electrical charge. Does it make sense? N, right? That's the number of electrons. Right? I think that's reasonable, very reasonable to assume that would be the situation. And we're going to kind of make it a little more accurate, but at least the logic should be clear that this is what. Right? And the speed at which they will carry the heat would be. So for example, here I can rewrite this electrical conductivity electrical conductivity as velocity, if you remember, is the mobility times the electric field, and electric field happens to be the gradient or the slope of the potential, electrical potential. Right? So you can write also electrical conductivity as electrical current as electrical conductivity minus negative of the gradient of the potential, which is the electric field, right? dV by dx. Similarly here, well, I'm going to first define the electrical thermal conductivity before we get into the details of it and split it into many terms. I think you can see why I'm writing this, hopefully, that you can think of it in one dimension as minus d temperature over dx. Right? But you can hopefully see the exact analogy to electrical thermal conductivity is here, right? Temperature gradient is what's driving the heat from one point to another. Potential gradient is what's driving the electrons from one point to another. Same concept, right? And so now we are asking how does the thermal conductivity, or what are the particles that are responsible for thermal conductivity? Here we had found that electrical conductivity went that way. These were the things responsible. We are now trying to ask what are the things responsible for thermal conductivity, right? And so there are a number of particles that are carrying the heat from one point to another. And what I'm going to do now is kind of zoom in into, let's say, a point here, which is x. Let's say this is x1 and x2. Okay. And zoom into that point. And I'm going to kind of sit here and see how is the heat being transported from my left side here to the right side. I want to see how is heat flowing from left to the right. And I think you can kind of figure out how this will pan out here. Remember, the number of electrons or the density of electrons is uniform. It's not like the density is changing. It's just the heat that's changing. But that means that electrons, because they are much hotter here, have a much higher velocity or speed, kinetic energy here. So this is, electrons are moving in all three directions, let's say randomly. But these electrons have much larger velocities than electrons right here. And I'll try to explain that. These arrows are just showing there are lots of electrons at that point, and they're moving in different directions because of the being kicked around by the heat and the lattice. Okay? And then I can, is that clear what I'm doing here? I'm just saying that electrons here are much faster than here. And but the electron density here and here, the number of electrons are the same. So I'm going to, let's see whether this makes sense what I write now. Okay? So I'm going to say that the heat current will be the energy at x plus, let's say x minus. So this point I'll call it as x minus a velocity of the electron times the time, or the scattering time before it relaxes, the same scattering time as here. So remember, it's going to essentially move, and then it scatters, loses some energy, moves again, and that's that is the value I'm going to use here. That's the energy of the electron at this point, x minus v tau, and this is x plus v tau. So the energy here minus energy here is the energy difference, and I'm interested in how does the energy move around, right? So how is energy transported from left to right? In fact, I know that the energy is just a proxy because it's more interestingly, it is the temperature locally here that is controlling the energy there, right? Does that make sense? I'm just trying to kind of make it more accurate now. So what is causing the difference of energies of electrons here and here is the temperature, because it's hotter on this side and it's colder on that side, right? This temperature. And then so that's the difference in energy between these 2 points. And just to be clear, the 2 points are separated by 2 times v tau. That's the distance, or that's delta x if you might. Right? And the heat current is the rate at which this energy is flowing from the left to right. Right? The rate at which the energy is flowing from the left to the right. And this much energy, this is the energy of each electron. So how many electrons are there? Well, n, but if they're moving randomly, only half of them are moving to the right, the other half are moving to the left. So at this point, I'm going to say it's n over 2, because only half of them are moving to the right. The rest are going that way. And so essentially what I'm going to do now is looking at the total flux to the right here. So we are going to only take this. And also just realize that the arguments we're going to use are kind of going to be approximate, because we're not worrying about factors of 2 and pi at this point, just so qualitatively. Okay? And what's very important is at what velocity are they moving, because the heat current is dependent on time, the rate of transport of energy, not just the energy itself, but the rate. So there's the velocity. Very similar to this. Yeah.
That velocity, though, is not constant throughout the metal, right?
That velocity is not constant. It depends on temperature as well. That's exactly right. And then we're going to actually take that into account. In fact, this velocity will be completely driven by temperature, mv squared. It will be of the order of kBt. We're going to see that soon. Yeah. All right. So that's I think kind of at least you can see what is the thought process in a very similar way to the electrical conductivity. This is an expression for the thermal conductivity. This is an expression for the heat current. Right? For the heat current. And so what I'm going to do now is essentially write it in this way, n over 2, and the velocity of the electrons. And I'm going to take this and say that, well, I'm going to bring them, imagine that these 2 planes are reasonably close to each other. And you can think of what we are doing now is going from a discrete step to a continuous derivatives here. So essentially, we're going to make that sort of an assumption, and you can see how it's going to work out. I'm going to just write that out first. What we have here is a difference in energies, delta E, right, which depends on temperature directly, but temperature depends on distance, right, because it's varying. And to make things all correct, so this is how I just want to kind of write this. I hope that's fine, right? Because that and that go away. This is just your delta E, right? And passing over to the limits of differential forms, I think you can now see what I'm going to do. I change them into derivatives, and my delta x is actually 2v tau, as I kind of present it out here. Okay, was there a question, Jim?
Yeah. Why is it n over 2?
Right. So the argument here is let's say I have 10 to the power. Let's say I have 2 times 10 to the power 22 per centimeter cube electrons at this plane, right? And because the velocity is because of heat, it's random. It's that means there are a certain number going that way, a certain number going that way, a certain number going that way. So if you want to find how many of them are going to the right, it's just half of all of them.
Oh, okay.
So that's just half.
Okay.
Yeah. Okay. So again, and from here, I'm going to just rearrange this. The 2 goes away, unfortunately. Yeah. And the velocity squares, and the tau comes out here. So you get something like that. And I'm going to do one more thing. This is the energy of each electron, all right? There's the energy of each electron. And I'm going to actually take the n here and write it as small n times E. So that becomes the energy density per unit volume. And the total number of electrons is basically total big N over the total volume, n over V. And this is a very important quantity. The total number of electrons times the energy of each electron. This is the total energy in the whole electron system. Total energy in joules. And so I'm going to take the volume back out, the manipulations. But this n times E is a very important quantity, and we'll encounter it many times later. This is the total energy of the electronic system, and this is du by dt. And this quantity here, does anybody know what is this called? If you basically take a solid of volume V and you give it a certain amount of energy, what is the change in temperature? This is called the heat capacity of anything. As you take electrons or atoms or whatever gas, right? Yeah. So this is called the heat capacity, and it's written as small c with a subscript of V, and the c sub V is the heat capacity per unit volume. So heat capacity per unit volume. Right. So this is an interesting result. So what we get is the heat current is therefore, we're going to write it in this way: heat capacity CV times the velocity of electrons V squared times tau times dt over dx. You can see it's starting to look like Ohm's law, but for heat. dt by dx is your temperature gradient, just like the potential gradient, right? So this quantity that's sitting out here is just one more step before I go there. The velocity that we are really interested in here, the velocity at which electrons are moving, is really the one, in one direction, v along x direction. We're looking at just one direction, because the electrons that are going in y or z, they are not contributing to the heat flow this way. Right? So it's really interested in unidirectional or direction-dependent Vx, and because of equipartition of energy, Vz squared is basically 3/2. So essentially, what I wanted to say is, because electrons are not preferentially going in any direction, this is half mv squared, right? So as a result, each of them is actually equal to the other, x, y, and z, and Vx squared happens to be v squared over 3. I think that's pretty clear, right? Square over 3. So really what we should have here is Vx squared, and that means I should have 1/3 here. Again, I made a lot of changes, so let me go back and change this as Vx, and then we're good. So this quantity here, 1/3 specific, the heat capacity times velocity squared tau, is defined now as the thermal conductivity of any material, of a metal. It's the thermal conductivity. And you can check the units and all that, but so essentially that's the thermal conductivity. And I'd just like to say is the heat current will really flow in the negative direction, so I should have a minus because I didn't take that into account here. So I should, this is x minus Vt, and this is x plus V tau, so we get a minus sign because of that. So heat obviously flows from hotter to colder regions here. So, all right. So the thermal conductivity is 1/3 this heat capacity velocity squared times tau. Okay, good. Yeah. Where's the 1/3 come from? Okay. So here the velocity that we must use is the x-directed velocity, not right. But in 3 dimensions. Yeah, it has x squared, y squared, and z squared. So that's 3. Yeah.
Why wouldn't it be 1/9 because it's squared?
Right. So let's see. So right, good question. So vz squared, right? And each of these are equal, right? So you get 3 times, say, vx squared here. Make sense? So, yeah. So get a. It's a kind of RMS sort of value. Yeah, root mean square. But okay. This is the thermal conductivity of the metal, of electrons in a metal, and the heat capacity of. Let me write down the next thing is electrical conductivity. We already know that. That happens to be what electron density Q squared. Did I miss something here? I think I did miss something. No, I didn't miss anything. Okay, fine. No. N e squared tau over mass of electrons. Okay. And now what I wanted to start out with today is that the ratio of these two is a is constant, right? And then that's what we want to find, ratio of this with the temperature. Yeah.
Where did the volume term go?
Okay, so I think I've been, so the volume is basically the specific heat is defined as per unit volume.
Oh,
Yeah.
heat per unit.
Yeah, per unit volume, it's per unit volume, yeah. All right. Okay, so now let's see, what we need to know is what's the velocity and what's the specific heat for electrons. And the specific heat of electrons in classical physics, in classical thermodynamics, is the way you find it is always we do 1 over V, the energy over dt. That's specific heat, right? And we kind of, and now the energy in classical thermodynamics of an electron that's free to move in 3 dimensions and is in equilibrium at a temperature T, the energy for every degree of freedom is kB T over 2. And if it's free to move in 3 dimensions, it's 3 over 2. That's the energy per electron in classical thermodynamics. It's the equipartition of energy. But you have big N electrons, right? So I'm trying to find what is U, and that is U. Right? That's the total energy of the electrons, right? So each electron has 3/2 kT energy, and then there are N electrons. Right? So that's the total energy, and I'm going to take a d over dt of that, rate of change of temperature, and divide it by the total volume, and I get my specific heat. Right? Very simple, right? Very simple, but please remember it because this is going to fall very soon. It's incorrect. For electrons, this is not correct. And this we'll see is responsible for the problems in Drude's model. We'll see that this 3/2 kT is not quite right because it violates Pauli exclusion principle and quantum mechanics. It violates them. Okay, but we're going to, obviously hindsight is perfect, so we can go with this now. It makes sense, of course. So N over V, again, we pull the N out again and bring it back. So we get 3/2 N times Boltzmann constant is my specific heat of electrons in classical physics. Very nice result, simple result. Right? Electron density times Boltzmann constant specific. Does that make sense what I did here? In case I'm missing terms, again, please let me know. Okay, velocity. Velocity in classical mechanics, if you have a lot of particles which have energy, again, free to move in 3 dimensions and all that sort of thing, I think we know that that's fine, right? That's the energy. Again, I'm not going to worry too much about other factors. There's some root mean squared, there's pi and all that. I'm not going to bother about that. Kinetic energy is driven by heat, and the velocity, therefore, is kBt over m of electrons. This is free electron mass. Okay, so let's take these 2 quantities and let's plop them in here. This and this, right? Plop them in here, right? And you can see now what you get is exactly that, that the electrical conductivity over, now what did I do here? Temperature. CV squared, yeah. So did I, okay, somebody should, sorry about this, okay. Yeah, thermal conductivity by electrical conductivity. Yeah, that's the ratio. So let's do that. Thermal conductivity over electrical conductivity times temperature is 1/3. Heat capacity 3/2 N times Boltzmann constant. V squared is kT by m. I think I probably did something weird here. And tau. Right, divided by electrical conductivity, which is n q squared tau by m of electrons, f of electrons here. Okay, so that's all, right? And I must have a temperature. This is the extra term here, and temperature goes with temperature here. Mass goes with mass. scattering time, the microscopic detail also cancels. Electron density goes away. Doesn't matter which metal you're talking about. All of them just cancel out magically, right? Threes go away. And I mean, there's some other details, but I think you can see right away where we are going with this. Electrical conductivity by thermal by electrical times temperature is equal to some constants, 3, and there's a 2 in the denominator, 3/2, right? Boltzmann constant over electron charge whole square, right? So that's true result, right? And that's interesting because you see, obviously these don't depend on which metal you're talking about, Boltzmann constant and electron charge, they are irrespective, and so that's the Lorentz number, and you plug in the numbers. I think I already mentioned that plug in the Boltzmann constant and plug in electron charge. You are right, very close. Right? So this was a kind of considered to be a big success of the fact that you can explain metals now. You can explain two of the most fundamental quantities about the metal, electrical thermal conductivity, and a deep connection between them. And you can see, something that had remained mysterious for half a century was beautifully explained by this theory, right? And then obviously the moment you give something like this to experimentalists, they're like, oh, I'm going to now measure the electrical or the specific heat and all that of electrons and find out what it is, right? And because now it's telling me that this must be correct. So I'm going to go and change my electron density in some materials, and I try to measure my specific heat. And when people started measuring it, this is what's called a null result. Basically, they find no matter how hard they try, this is incorrect. They just had very, very low numbers of specific heat of capacity. So you can see it's something weird because it's explaining the Wiedemann Grand Law and the Lorentz number beautifully, but there's something intrinsically problematic in this situation. There's no specific heat of electrons. In fact, it's very, very small. And what we're going to see now is this is also one of the kind of opening the Pandora's box now, because it's saying that there's something deeply wrong about all our assumptions at this point. And we'll see later how things cancel out, but what we'll see today is, actually we won't see it today, but we'll see in the next class that the specific heat of electrons is not given by that, but it's given by something close, and what enters here is another term which looks like this, okay, over the Fermi energy. You're going to see that. It's very interesting. And this Fermi energy has Planck's constant, which is the, wherever you see Planck constant, there's quantum there, right? So it's going to sit inside there. We'll see this. So we'll see that. And what we'll see is that this factor for metals, this factor kT at room temperature is 300 Kelvin or so. EF is like 10 to the power 5 or 10 to the power 4 Kelvin. So this factor is really, really small. kT over this. Very, very small. And this is real. I mean, this is the correct electronic specific heat of electrons. It's not just that. In fact, to be more accurate, let me just write down the exact result from quantum mechanics. It's pi square over 3. This is the quantum. And we're going to see that now. And that, and that took a, by the way, and Drude's result, came around 1900, but it took another 25 years, quarter of a century, to go from here to there, because people had to discover quantum mechanics first and understand electrons are quantum mechanical objects. They are subject to quantum mechanics, not to classical mechanics. So it took, a quarter of a century to go from here to here too. Right? And let's look at that part of it. Let me just say that the reason this happens is, qualitatively, it's actually very straightforward to understand, but quantitatively, obviously, you have to invoke quantum, and this is what we are going to use in this course to motivate our quantum part of it. Those who had taken lasers would realize, quantum started with light. We are going to motivate it with electrons here. So yeah. Okay, so the reason this happens is, in classical mechanics, if you have electrons and you say, how are the electrons distributed in energy? How are they distributed in energy? I have electrons with very low energy. I'm going to say how many electrons are there at any energy E. Right? Electrons with very low energy, I have electrons with very high energy. And classical mechanics always says the same thing. Classical statistical thermodynamics always says the same thing. If your energy is E, the occupation probability is e to the power minus E over kT. This is classical thermodynamics. Right? So if I make a plot of this, it looks like this. It goes very high at low energies, and it goes like that. Right? You can make a plot of that. And this is the Maxwell-Boltzmann distribution, right? Or Boltzmann. And this is what defines your Boltzmann constant almost, right? Right? And if this is so, and I have this bunch of electrons, right? And I give it some heat, right? I give it some energy. Give it some energy. What are we trying to explain? CV, which is du over dt, 1 over v, right? And so I'm giving it a certain amount of energy in joules, by whatever means, electric field, whatever be it. Yeah? And now I want to find what is the rate of change, what is the temperature rise, for example, and then things like that. That's really the meaning of this heat. So you can see that if I give heat to this object, to this bunch of electrons, these electrons can go to a little high energy, these electrons can go to high energy. So all of them kind of equally respond. They can all heat up, gain a little energy. Does that make sense? All of them can. And that's why you have N sitting at here, meaning you have all the electrons equally taking in that heat and raising their energies. And what quantum mechanics will tell us is that is incorrect, because electrons are fermions. They have this behavior that you cannot put two electrons in one energy state. Impossible. And that's Pauli exclusion principle. And what that's going to do is profoundly change this distribution. It's going to make it the maximum value you can ever achieve is 1. Right? Maximum value is 1. And it's going to go fill up electrons. If you have a lot of electrons, it just so happens you got to keep filling because you can't go above 1. Keep filling, keep filling, keep filling, and then you run out. That's your distribution. This is the heart of quantum mechanics, really, and you have probably seen it many times. This is the Maxwell-Boltzmann distribution of electrons. This is called the Fermi-Dirac distribution. And the Fermi-Dirac distribution, and it looks like 1 over 1 plus an exponential of the electron energy minus what we're going to call as the chemical potential over kT, kBT. That's how it's going to look. Right? So, and this is one of the most important results in this course, at least, of quantum mechanics, that essentially this comes about because of the Pauli exclusion principle, that you can't put two fermions in one orbital or one electron energy state. So that's the meaning of it. And from here, you can kind of at least qualitatively see why the specific heat must be like this. Because if you give a lot of energy to this distribution of electrons now, right? These guys can never gain any energy because they're already maxed out. You can't fill anymore. Not allowed, right? So the only ones that will respond are the ones kind of out here in the very top. Very top, right? Because they have some empty states to get into here, right? And that window is of the order of kBt, whereas this entire window till where you're filled is the Fermi energy EF. So you get only a fraction of this slice divided by the whole thing, which is kT by EF. That's how you can excite. That's why specific heat is really, really small compared to what you initially thought. Does that make sense? Yeah. So I've not explained to you, why this happens, but if this is so, at least you can understand this part. Right? So, is that clear? Or any questions? All right. If not, let's see why this happens, and that's going to lead us to a quantum. So we can spend the rest of the class today talking about quantum mechanics and how it leads to the Pauli exclusion principle, and how does it result in Fermi-Dirac distribution and all that. Is that okay? I can stop and answer any questions that might be, because we're going to kind of take a detour now. All right. If not, let's move forward then. So while I'm erasing, just to summarize, Drude's model for electrical conductivity beautifully explains electrical conductivity of metals. There are actually quite a few things it doesn't explain, but I didn't get into that. It explains the thermal conductivity, and it explains the ratio of the two. Why is it independent for most metals? And all that it did was took all the knowledge of physics before him and added to it that there is an electron with a charge q and mass m, and then you get all this stuff right away. And now what we are encountering is some of the things that went into his calculations, for example, the electronic specific heat and all that, is incorrect, because experimentally it doesn't work out that way. When you measure it, it's way smaller. The capacity is way smaller than what it is, and now we want to see why is it that the electrons follow Fermi-Dirac distribution, and where does the Pauli exclusion come from, and all that sort of thing. So, okay, so we're going to do a really short, kind of a crash course on quantum, but we'll kind of select out all the things that we need for this course, and kind of go with that. All right, so the quantum really starts, with photons, really. I mean, that's where it really started. The Blackbody radiation, and was unexplained mystery for for a very long time, and I just write a couple of things first. So Max Planck in 1900, I think, or 1901, I forget. What he essentially, I will just summarize this quickly and not get into too much detail about this here. But if I look at the energy of radiation in electromagnetic field of light, and you plot it as a function of how many photons are coming out as a function of energy, it follows this sort of a pattern, Blackbody radiation. And I'm not getting the details, but suffice it to say that what he needed to explain that why is light or Blackbody radiation, the energy density as a function of frequency of light behaving in this way, the postulates that he had to come up with is that the energy of a photon is a constant times the frequency being the circular frequency, is 2 pi times the linear frequency in hertz, and this is circular radians per second. And the second thing is that the momentum of the photon is times k, and so let me write those things down. And this is kind of the postulate of Planck, and based on that and some thermodynamic arguments, you can explain the Blackbody radiation. I'm not getting into that at this point. Okay? But so essentially, what he said is, if a photon has a frequency omega, which the frequency of a photon is always related very closely with the speed of light itself, right? C and wavelength. So they are always locked by this relation, right? Speed of light is wavelength times the frequency. So, but it was very strange to write down that photons must have a momentum, and because, well, they're extremely light. In fact, they're massless. Their mass is 0, right? And around the same time, Einstein was developing, completely parallel, separate approach. He's developing relativity, the theory of relativity, right, of stars and moons, and explaining. In fact, the reason Einstein was developing relativity is trying to understand light as well, just like Planck. And in relativity, if you write down the momentum of any particle which has a mass, this is classical relativity. This is the classical result. Newton says that momentum is mass times velocity. Right? But Einstein said that is incorrect. It's not the correct expression, because there's something else that's missing here, right? And what's missing here? If anybody can help. Yeah, there's something in the denominator, right? And that happens to be 1 minus v over c whole squared, because velocities are not absolute, and that sort of thing. So it's all relative, because, as you know, depending on what frame of reference you're sitting in, it depends. I mean, velocity, you could be 0 because you're moving with constant velocity, and somebody could be moving with you, and your velocity is 0 for them, right? So it's not an absolute quantity. Anyway, all right. So that's the real expression for momentum. And the way Einstein explained Planck's photons, this discrete quantity that carried energy is called the photon, right? And the packet of energy with h bar omega energy. But it has a momentum p, right? But if you look at Einstein's expression, if your mass is 0, you can't have a momentum, right? Except there's only one situation when you can. There's only one situation. You can see when the denominator blows up, right? When the denominator goes to 0, right? So any particle that is massless to have a momentum which is non-zero must have v equal to c, right? Only then it can have a non-zero momentum, right? So it's actually what Einstein is trying to say is his stuff is consistent with Planck. Right? So it's consistent. So any particle to have, anyway, does that make sense? If a particle is massless and it must have a momentum, it must be moving speed of light, meaning it must be light itself. Right? So that's the meaning of light itself. Right? So, and in fact, Einstein used this to go much beyond, this just analogy. He used the concept of Planck's photons to explain photoelectric effect, etc., etc. Right? We're not going to get into that. What I want to get into is the nature of photons and how is it motivating the nature of electrons and how does it explain Pauli exclusion principle and all that sort of thing that we need for this course. That's what I want to kind of get to. Okay, so how are we doing on time? 12:55. Okay, we have a few minutes, so we should be able to finish this section today. So if you take photons, I'm going to do analogy of photons and electrons now. And let's say I have a source of photons. Today, this is exclusively done with lasers of one wavelength, fixed wavelength, therefore fixed frequency as well. I'm going to take a laser that's spitting out these photons, and I'm going to put it in front of it a diffraction pattern or a double slit. I think you have probably seen this sort of a thing many times if you've done quantum, but we're going to put it in the way of the photon. And I've made my slit such that the distance between the openings is of the order of the wavelength and all that, so that I'm kind of trying to force it to diffract and all that. Right? So, does that make sense? So now I put a screen on this side, right? And on the screen I put thousands of semiconductor-based photodetectors so that I can catch the photons as they hit the screen. I like to think of it, so this laser is made of semiconductors and that's also made of semiconductors. So I think we are in business in this experiment as engineers, right? So, all right, so this is an array of CCDs or some photodetectors, and here's a laser that's emitting photons. And now I think also in high school you learn how that the way you will kind of detect signals and you can count the number of photons, and what you will detect here is an interference pattern, right? All right, so I don't know, something like that. So what am I plotting here? I'm plotting the number of photons integrated over a certain time, right? Is that clear? Or right? So why is this happening? So you track one photon here and then you go there, you track another photon there. So they have a certain path length difference, and the path length may be different by one wavelength or a half a wavelength. If it's different by one wavelength, you have constructive interference. If it's different by half a wavelength, you have destructive interference, right? And so you get maximum, minimum, and all that, right? So, and that's a classic wave mechanism. It has nothing to do with quantum mechanics whatsoever. Right? Any wave will do that. You can have, water, and you have two openings, and you kind of, create waves, and you go across, and you get this, right? Does that make sense? So it's nothing to do with quantum mechanics whatsoever at all, right? Now, where quantum mechanics kicks in now, all right, so when quantum mechanics kicks in now, what you do is you kind of tune down the laser now. Turn it down. Turn down the intensity. So what we are plotting here is the number of photons, right? Let's say this is 10 to the power 4, and this is maybe 10 to the power 3 and 10 and so on, 1,000 photons. Now you go down to just one photon, and let it go, right? So now what's going to happen now, right? So a detector. So what will happen now is just one of the detectors will detect the photon, not all. It's not like this detector will detect 1,000th of a photon and that will detect 1,000,000th. It's not like that. The entire photon, the entire energy of the photon goes into one detector, right? And it vanishes. It basically dumps all the energy into one particle. So what does that mean? That's a very much unwave-like characteristic, right? It's a particle characteristic that all the energy is concentrated at one point now. Right? Does that make sense? Yeah. So that is really the heart of quantum mechanics. That photons are behaving like particles. That only one of the detector goes off, right? And when that happens, you don't have any pattern whatsoever. You just have a 1. That's it. There's nothing else. Right? It's 1 or a 0. Right? Then then you ramp it back up, or you kind of start repeating this experiment many, many times. You repeat it 1 billion times, let's say. And you do all your counting, and you plot the histogram, and what you see now is the histogram is going to look like that. And that's kind of the crazy part of about quantum mechanics, that it's not like the photon that went out now remembers what happened to the photon that went in there yesterday. It's not like that at all, right? It's just that this particle that's moving along, or wave that's moving, has associated with it a certain amount of wavelength. And that wave, whenever it goes through, it kind of gets stuck or interferes with this every time it goes, right? And so statistically, when I do it 1 billion times, I'm going to kind of recover this again, right? And that's, so a photon is behaving like a particle in this experiment. Is that clear? I mean, that's one of the fact that it forms an interference pattern is really classical physics, but the fact that it hits and excites only one detector is completely quantum, right? Okay, and that's Einstein stuff. I mean, so energy goes in one quantum, and it kind of goes in there. Now, what we're going to do now is for electrons and ask the same question, and this happened, by the way. So historically, 1901, 1905 is when the quantum hypothesis came along. But for the real quantum mechanics to come along, with Heisenberg and Schrödinger and Dirac, it was another 25 years, quarter century after this, because all the stuff happened in 1926, 27, Heisenberg first, and then Dirac and all that, and Schrödinger. So it's not like this happened immediately, because people still didn't think at all that electrons are quantum mechanical objects at this point, right? But experimentally, what they did know was people had measured that if you take the hydrogen atom, which has a proton and an electron going around it, right, and you shoot light at it and see what comes out is a series of very sharp lines, right? Very sharp lines. And by that time, Thomson and others, they knew that all atoms have electrons, so they knew there are electrons going around, right? And Rutherford came along and found there was a nucleus and all that stuff, right? So they discovered the atom. The nuclear physics started and all that at that time. But when they look at the electrons, they're only emitting at very sharp lines and not as a continuum, right? Not as a continuum, because if you take any classical particle and let it go, it can have all energies again, right? Why is it that it's just going in discrete quantities, right? And so this is what kind of kept people very busy, didn't quite understand till Heisenberg came along and changed the game a little bit. So I'm just going to say the Heisenberg story as an aside, because we are going to go with Schrödinger's picture, not so much of the Heisenberg picture. What Heisenberg said is the energy, let's look at a very simple classical mechanics problem. Let's say a mass and a spring. You have kinetic potential energy plus half mass times dx over dt whole square, right? This is the kinetic energy and the potential energy of a mass spring system. This is an aside at this point. We don't want to get into too many specifics of this. And for a classical system, this is always continuous. You can't do anything about it, right? I mean, it can take in any x. It can be anywhere in space. It can take on any velocity. It can have any momentum, mass times velocity, right? So it's both are precisely defined and they're continuous quantities. You can't change them, right? That's classical mechanics. And Heisenberg said that I know that in mathematics, discrete values of energy will come if the energy is not a continuous function, but if it's a matrix. Because a matrix has discrete eigenvalues that you need, right? And so he said that he kind of, as a result, developed what's called the matrix mechanics for quantum mechanics, matrix version of quantum mechanics. Right? He said that my x, it must be that the electron space is not clearly defined, which means I cannot define a number for it. I have to define an array of numbers. And that's a matrix. Right? So it's essentially what he said, that there's a little probability of finding an electron there, little more, little more, little more, little less, little less. So essentially what I now get is a matrix of, say, 0.1, 0.2, 0.8, 0.6, and all that. So he changed x into a matrix, momentum into a matrix, x and p, and that's where the Heisenberg uncertainty principle comes from, because numbers always commute. X and p will always commute, but the matrices most likely will not, right? A times b is not equal to b times a and all that. So that's where that stuff comes from. We are going to look at the Schrödinger picture, which is slightly different. Later on, when you are going to calculate band structures, from tight binding model for semiconductors, you are going to use effectively Heisenberg's model, but we're going to start with Schrödinger. Okay? Yeah. So essentially, both x and momentum, instead of, I think the best word that Max Born uses is it's not a number but a scar of a number. It kind of gets stretched out, So and the reason for that we'll see now is because electrons are also waves, just like photons are waves, but they're particles. Electrons, which are thought to be particles, have also wave-like behavior now, right? So that's the idea, and that's why you cannot define a precise location, but some sort of a wave packet that kind of looks like that. Yeah. Okay, so now we go back to this experiment and shoot electrons at periodic grating like that, and we have electron detectors on this side, and we're looking for electrons. Right? And what you'll see now is if you have lots of electrons, it will again form. I mean, classically, I think you can really see that this should lead to some sort of behavior like that, and that should lead to a number of electrons that are like that, and the total should be like that. That's classical mechanics. Right? And indeed, I mean, if you have the example is, I think a great example that is used is you are standing here, and somebody's shooting bullets, but there are two holes, right? And you obviously want to be as far away, and not get in the way. But if if these particles are really behaving like waves, then I think that it will really do this sort of a behavior now, right? So and indeed, I think in perhaps next week we can go over and see this in work in the Duffy lab. We kind of use this electron diffraction pretty much every other day in our experiments in the lab. And this is indeed this is what happens. And then let me first say that it's also extremely weird because you can see that from a particle viewpoint. Right. So initially, if it was classical mechanics, it was something like that, right? And if it's quantum, now it's going through these ripples, right? And if the mass is heavier and the wavelength gets shorter and shorter, so you kind of don't have equipment that can resolve it at that level, right? And the mass of the particle plays a very big role in what is the wavelength of the particle. So, so this was Planck's hypothesis for momentum of particles, and you can write it in a slightly different way. You can write it as h bar is h over 2 pi. H is the original Planck's constant. K is 2 pi by the wavelength, right? And so you get is Planck's constant over lambda is equal to the momentum, right? This is true for photons, and almost 10 or 15 years after Planck, the French physicist de Broglie comes along and says that in his PhD thesis, his very interesting argument. He says that this looks like a relation that shouldn't be restricted to photons itself. It should be true for everything, also things that have mass, because obviously we know that Newton's laws say that particles with mass do have momentum, and Ollie said that this must be true not just for photons but also for electrons, for cars, for spaceships and planets as well. I mean, sorry, I think it's upside down. Yeah, h over p. Yeah, momentum, right? And so that's de Broglie relation. It's just a hypothesis, and it took till 1926. When in Bell Labs in New York, these two scientists, Davison and Germer, so what they were doing is they were studying vacuum tubes. That was essentially all right. So what they were studying is a piece of nickel like this, and then they had detectors around. Sorry, let me draw it a little more accurately. Okay. So it's a piece of nickel, and I think I'm not going to do justice to this, but I'll try my best. Yeah. And they had electron gun here, and a piece of nickel, and they had like a phosphorescent screens around here, and they could detect if there is any electron that hit, and this is all vacuum inside. And there a piece of nickel, and then essentially this sort of a structure is what's called a vacuum tube. It's used for electronics, for amplification. For at that time the Bell telephone network, that was before transistors, right? Before semiconductors, and they were using vacuum tubes as amplifiers of signals. You have a little, AC signal come in, and because of this vacuum and electrons going across a grid and all that, you could amplify that signal at a high frequency. Enables phone calls. I mean, at that time, that's what they're doing. They were making phone network for the US, right? And so what they find is this is a piece of nickel metal, and they were looking at, if you again do this sort of an experiment. So this is your array of detectors, if you might. Array of detectors, right? And they had a piece of metal, and they were essentially shooting electrons and seeing what's coming out, and then if they're plotting it, and it was looking more like classical, it was kind of roughly uniform. But what happened? They had an accident, and this glass jar which had vacuum developed a leak. So they developed a leak, so they repaired it, they fixed it, and just to make sure that there's sometimes oxides that form on surface of these metals when you expose it to air. So what they did was they kind of heated this up by passing electrical current through it and melted it pretty much, and kind of almost melted it, and it recrystallized. It recrystallized. And when it becomes a crystal, and you zoom in into this, a crystal is basically a series of atoms, right? Right? And that's where we're getting into solid state now. So, and it's a series of atoms, and remember the electron is coming along, and look at this and this. There's your grating. Right? It's a periodic arrangement of atoms in a crystal. Right? And so what they observed was, for them it made no sense, but they observed that initially they were seeing this sort of a uniform distribution of electrons that were bouncing off. But after they recrystallized and kind of cleaned out and made it a crystal, it became, they observed the diffraction pattern like that here. Right? The electrons bouncing back and creating a diffraction pattern. And they, if you read through the history, I think Davison was visiting some conference in Europe, and then he saw de Broglie's thesis. He's like, well, I think this is what we are seeing. And it took 10, 15 years after de Broglie for this to come along and say that, well, electrons are behaving like waves. Right? Because if you apply de Broglie relation, you can exactly explain all the wavelengths they saw. Yeah. And this is today routinely used to measure the distance between two atoms. It's crystallography and all that stuff. So we track the electron diffraction patterns through this. Okay, so de Broglie relation says that particles are waves, and that's essentially really the birth of quantum mechanics, because now one might ask the question that if you have an electron with a mass m and a charge q, what laws of motion is it subject to? How does it move if I apply force to it, right? Because classical mechanics is only restricted to particles, right? Not to waves, right? Does that make sense? I mean, Newton's laws do not say how a wave-like object might move, right? So this, and that's wave mechanics or quantum mechanics and stuff, right? So I'm going to kind of spend the last, roughly 5 or 10 minutes. How much is it? Yeah, 5 minutes, kind of motivating the wave function, and we'll take it from the wave function in the next class, right? So the idea now is you have a particle, but along with the particle, which is the electron is nothing like what Drude had assumed, that it has, it's a completely classical particle. But now we are seeing that because of its motion along certain direction, because of a momentum p, it also is dragging along with it a certain wavelength, some wavelength associated with it because its relations. So if the momentum is p, Planck's constant by this is the wavelength, right? So it's dragging along with it a certain wavelength. You can almost think of it classically, because it has a wavelength, it kind of gets tangled up and interferes, and does. So actually it is correct, so that's way of thinking is correct. And if something has a wavelength, the problem now is if you have particle in one dimension and it has a wavelength, and you ask what is the, let's say you say it's moving with a momentum p, and what is its location x, right? You can see there's a problem because it has a wavelength. You cannot define a precise location, because a wave, if you had a wave, it really goes forever. Really, the moment you cut off the wave, you can create the best you can create instead of a pure wave. A pure wave would have a form like e to the power I k times x. That would be the functional form of a wave in space. Right? I think you've seen that, right? What is k? It's the rate of change of phase, or I 2 pi over lambda times x. So you can write it as x over lambda, right? So e to the power I. So every one wavelength, you change the phase by 2 pi, right? So you're kind of going, in cycles, right? So you're changing the 2 pi. Every time your x moves by a wavelength, your phase changes by 2 pi. Right? So k is the rate of change of phase. But so for a wave, now I'm talking about an electron, which is a wave according to de Broglie and Gavison-Germer experiment. The question is, what is x? Because you cannot define precisely what is an x for a wave, right? So you can go successively, closer and closer. You can go down to one wavelength if you might, right? Almost. You can go down to one wavelength. But anything shorter than that, you have lost all identity as a wave. Right? It's not a wave anymore. A real wave is infinite, right? That's really what we're trying to say, right? So it's infinitely spread out and it has no precise x. And the best you can do is take a bunch of these waves with different wavelengths and take C1 times a longer wavelength times C2 times a shorter wavelength. You can combine all of them and create what we call as a wave packet. You can kind of try to create something like that. That's the best we can do by combining let's say Ck e to the power I kx k. Right? So we're summing over many kinds of wave vectors or many kinds of wavelengths. K is just 2 pi by wavelength, right? So it's an index. So we're going to kind of look at this in more detail later. So I'm just trying to kind of motivate why do we need a wave function. So what we are trying to now say is that the location of this particle, because it's definitely a particle, but it also has wave-like nature, is kind of gets smeared out by delta x, at least some delta x at this point. Right? And that delta x is very much related to how fast is that particle moving, and what is its momentum, right? And this is really the relation. And let's just write it. If you had just a wave, then I think you can show that for all distributions of all sorts of combinations mathematically you can take here. Then if you consider the wave k is equal to 2 pi by lambda, right? Then the distance over which you're uncertain here by the change in how many momenta. Let me just sketch this too, right? So k. If I had only one wave, you'd have a very sharp k, right? It has one wavelength. I take another one, I take C1 times that K1. I take another one with maybe some other weight, C2 times that K2, and C3 times K3, and I sum them all over, and I create the wave packet now. Right? So now I have also got a spread in K space now. Right? That's my delta Kx. That's what I mean by that. Right? Right? To create a wave packet, you must spread out in K space too. Right? Right? And this too, when you take the product of it, so if I want to create a very short wave packet, you can see I need a lot of Ks here, right? I need a lot of Ks. If I want to create a very soft, long wavelength, then I just need one and very little of others. Does this make sense? So, right. Okay. So, and mathematically, you can show that the function that if you have a Gaussian instead of this sort of, then you get a half here, and Planck's constant multiplied by K is momentum. So Heisenberg's uncertainty relation is really essentially a result of Fourier's law too. There's no. So momentum and space get uncertain. How precisely can you define is greater than h bar by 2. That's the uncertainty relation for mechanics. And because your quantum in quantum mechanics now, in classical mechanics we had that here's real space and here's momentum of a particle, and it's moving along, say, that line. And in classical mechanics, you can say that I have a very well-defined trajectory, right? I'm going to move. I know at every point of time what is my x and what is my momentum. At all points of time, I know that. And there's a law that's governing its future as well. And that's Newton's law. It's saying mass times d2x over dt squared, right? If I know the force, I can not only say where is the particle now, I can say where it is going to be till eternity, right? As long as I know the force, right? That's classical mechanics for you. So you know both x and p precisely. You can ask the question, what is the energy of the particle when it was here, right? Energy is also precisely defined. Half m, let's write it this way. Momentum squared by 2 mass plus the potential at that point. Precisely defined. There's no unknown left, right? That's classical mechanics for you. And now if you want to ask this question in quantum mechanics, you're in big trouble. Why? Because x and px cannot be defined precisely at the same time. It cannot be, right? So, and x and px are not numbers anymore. That's what we're trying to say. So that's why, Schrodinger realizes that, and he says that I'm going to give you a prescription to find the energy, and that's the Schrodinger's equation, right? So we're going to see that. But essentially, because x and momentum are not numbers anymore, I mean, they get uncertainties around them, they have become functions, and the state of the particle in quantum mechanics is kind of, if you want to consider it this way, it's smeared out. It's like a blob here with delta x and delta px. It's a blob, and that's moving. The whole blob is moving according to the laws of Schrodinger and quantum mechanics now. But that's the main idea. And the state of the system, the electron itself, or electron system, be it in a metal, in a semiconductor, is not going to be defined by the pair of numbers anymore, but by a function, right? And that function must have both these quantities in it, x and px. It must have both. Does that make sense? It must, because they are tangled up now because of this relation. They're connected, right? And that is the wave function of the particle. And we're going to start from here in the next class. And so that we'll see that the wave function of a free electron is very simple, but it's also profound at the same time. It looks like that for a free electron. And it is necessarily going to be a complex number for a free electron. It's a complex quantity. We'll see that you cannot get away from that fact that it must be complex in order to satisfy the fact that it's a particle and a wave. Okay, good. So we're going to start from here, and in the next class we'll see, after 2 or 3 steps from here, you'll realize that there can be 2 kinds of particles. There's fermions and there's bosons, and fermions must satisfy Fermi-Dirac distribution, which resolves the problem with Drude's theory, and that's the beginning of the modern condensed matter solid state physics pretty much. And we'll apply it to semiconductors, and we kind of go from there. Okay, so meet on Thursday.